Assalamu alaikum wa rahmatullahi wa barakatuh. Chapter 7. Chapter 7, it is structuring system requirement. So far we've done the following. In chapter 1 we talk about introduction. Introduction, what is system analyst, what is information system, what is the SDLC, all the phases of the SDLC, system development lifecycle, identification, selection, initiation, planning, analysis, design, and implementation. Then we talk about the alternative for the SDLC. The alternative is the rapid application development. We talk about the case tools. Then we talk about extreme programming and rational unified process, whatever, as alternative, But actually they are not, because system development lifecycle, it is a methodology. But most of these are really processes. And the methodology, it's really different than the process, at least in my opinion. When we talk in chapter 5, we went there to initiation and the planning. Initiation and the planning, it is the first phase we are going to cover in this class. But actually, identification and selection is the phase which it is we don't really take in this class. That one, as we said, who identify the project. Identify the project, all the stakeholder could really identify. Then we prioritize them, categorize them, and then select them. We as an IT team, IT community, and the business community, chief executive officer and manager and whoever, from their part. Then after initiation planning, after we initiate the team and we establish the procedure, how really we're going to deal with the customer, then we want to try to build the baseline project plan. Baseline project plan, it has introduction about the program. Then we find out what is the scope, what's the boundary of our system, and we build a context diagram, and around it, those stakeholders, the external entity, the people and the system who are dealing with that project. Then we went there, after we find out the boundary of the system, we could find out the risk, what risk we might have, which stops us from accomplishing the project. Actually, the risk, there are many different types or categories of risk, like, we take them in software engineering. One of them is product risk, project risk, organization risk, etc., etc. The one really we concentrate, and the one really it's important for us here as our project is really education project, it is the project risk. What are those risks which it is they could stop us from finishing the project on time? Then after that, after the risk, we could find out feasibility. Is it feasible or not? There are many different categories: financial, schedule, technical, whatever. Again, in our project, in our class project, we concentrate on two. One of them is the schedule. Is it really schedule feasibility? Could we finish that project within the time frame we have? And the other one, or the other category, it is the technical feasibility, which it is, are we technically able and capable of doing that project? And the other question is, there is a technology, is the technology we are going to use to accomplish the project exist in our environment or not? Akhiran, we did the timeline. We did some estimation, a quick estimation. We used, the estimation of pessimistic, optimistic, and most likely. We find the time estimate. Then we build the Gantt chart. The Gantt chart. From the Gantt chart, we found, if it is a critical, we found the critical path, etc. Then we went after that to collect requirement. Actually, before collecting requirement, we develop or we build the baseline project plan, which it has all the information. We present it to the customer, and then after that, when we present it to the customer, they sign it, and now it is an official document. If everything is okay, so we continue and we proceed going to the analysis phase, which it is the first one, or the first phase, or the first activity of the analysis phase is collecting requirement. As we said in software engineering, requirement elicitation actually. Requirement elicitation, not really collecting or determining whatever had. Then after that we found, a traditional method to collect requirement from like interview, questionnaire, whatever, and then we talk about again the traditional method like the prototyping. Then we talk about the disruptive technology, the business process reengineering, and then. Now we have all the document, all the requirement with us. Now we have to go and structure. Chapter 7, structuring system requirement. Actually, in structuring system requirement, we have two different things. One of them, the process modeling, and the other one is the logic modeling. And we used to have these in two different chapters, but I put them together, in one chapter. The process modeling, it is we taking the context diagram and then we decompose it, we explode it down until we get the lowest level of DFD, which is the primitive DFD. In other words, we take the context diagram of us and then the scope, the boundary, and then we explode it to the pieces, the small piece, which is a function or a program, the one we are going to write. We write the program, we write the function, and we put them together, integrate them together, build them piece by piece, bottom up, until we get the whole system. Now, what really we are trying to do here is going to the context diagram, explode it, to level 0, which is the major entity, as the one we're going to see in a few slides. And then after that, we explode it further and further until the end. The second part of this chapter, it is the logic modeling. The logic modeling, it is, there are two different or three different models: pseudocode, decision table, and decision tree. And we'll see in the coming lecture what really we are talking about here. Now, after we finishing the introduction for this chapter, which it is explain the whole story of our course from first chapter, fifth and sixth, and now we're talking about seventh, we want to see what is really the objective for this chapter. First of all, understand logical modeling of process by studying example of data flow diagram, which it is the data flow diagrams. Data flow diagrams, actually context diagram, it is like a data flow, because the rules we use to build the context diagram, it is the same rule we use it for data flow diagram. And draw data flow diagrams following specific rules. There are some symbols and notation and rules for that one, so we have to understand and find out what's the alphabet we use here, what really the component of the data flow diagram. And actually there are symbols, 4 symbols. One of them is the square, which it is source or sink. One of them is the rectangle, which it is represent a database or file or whatever. And one of them is the oval, which it is represent the process, and the arrow, which it is represent the data flow, data in motion from one symbol to another one, from process to a process, from a process to sync, from process to a database, as we see in the future slides. Decompose data flow diagram into lower level, balance, as we're gonna talk about it later on. More objective, it is use data flow diagram as a tool to support the analysis information. And we see how really we're going to use the data flow diagram as analysis tool when we try to compare the level of a DFD with the level beneath it to see it is really balancing or not. All the data flows, the in and out, are the same, and we'll see it soon. Discuss process modeling for electronic commerce application, electronic commerce, which the one, we'll see it as an example, and then we are going to use decision table, decision tree, and pseudocode. All these we're going to use them, as a logic modeling at the end of this chapter. When we look at this diagram, which it is really have the process modeling. It is really like the system development life cycle. We show here the major phases there, which it is the planning. Then we are done with the planning, the analysis we are going to do. We did already requirement determination, requirement gathering, requirement elicitation, and now we're working in the requirement structuring, which it has the process modeling and the logic modeling of it, as we said earlier. Then after that, we go to the design. The design we are going to take just before the in the analysis, we have something else, which it is data conceptual modeling. Data conceptual modeling, what is the ERD, entity relationship diagram. After we finish the analysis, then we go to the design phase, and we cover there the interface design and the database design. Then after that, and we have the architecture design, the one we covered already in the software engineering. So we have three different things, three different types of design: the architecture design, as we learned from software engineering, the database design, or the interface design. After we finish all the design phase, then we go to the implementation. Implementation, it has many different activities: coding, inspection, data conversion, finalized documentation, and installation, the last one when we install the system. And after that, with the system development life cycle as an iterative cycle, we go to the maintenance. But actually the maintenance, the development methodology, it is done. But the system development life cycle itself, now it goes to the maintenance, as we see it in this diagram. Process modeling, what is the definition of it? It graphically represent the processes that capture, manipulate, store, and distribute data between a system and its environment and among system components, which it is in all these functions: capturing, manipulate, store, and distribute. Distribute, capture, maybe just take it as an input. It comes from the source to go to a process. This is to capture the information. Manipulate it, the process, do some calculation to it, and then store it, probably if there is a need to store something in the data store, and distribute it to many different reports or data store or whatever. Then utilize information gathered during requirement determination. Actually, we take the requirement, we gather it in the requirement determination according to the business rule, whatever, and we handle it, model, process, and data structure, as we talk about it. What really the deliverable here, for this phase? First of all, the context diagram, the context data flow diagram, the scope of the system. Remember, we said the context diagram, it is a data flow, because it represents, the symbol we use, it is really the same one in the data flow diagram. Context diagram, it is the name of our project in oval or in a rectangle, and the external entities comes around it. Then the FD of the current physical system, adequate detail only. We take the current system and we see what really the DFDs, if there is any. The FD of the current logical system, as we're going to see again, as we're going to see later on, and enable analysis to understand the current system, whatever it is. When we talk about the physical system, the current physical system, it is the people who's going to work, who's working in the system. Because the first thing when the customer want to explain to me what really the system is doing, he usually mention either technology or mention a person who's doing this. Then the logical will take the technology and the person, and we replace him with a process. Now we continue with deliverable, the FDs of a new logical system. After we took, and as we said before, the current physical, we turn it to a new current logical. Then now any change to it, any extra flow diagram, any extra data flow or process, deletion of something, addition of function, whatever, we put it there, and we come up with a new logical system. Technology independent, show data flow, structure, and function requirement of a new system. Thorough description of each DFD. This is, for the DFD, there are many processes, there are many data flows, whatever. All these terms, all these things, I think we should describe it and put it in a data dictionary if we have, or in any documentation package we have. Data flow diagram in mechanics represent both physical and logical information system. Only 4 symbols are used. The 4 symbols here we use in the data flow diagram are square, which it is represent a source or sink, as we can explain in the future. Then the oval, which is represent the process. Rectangle represent a database, data set, whatever, the one we create. And the data flow, which it is an arrow. And in the arrow with one direction only, because it's flowing from from one thing to another, from a source to a process, from a process to a sink, as we're gonna see shortly. Useful for depicting purely logical DFD that detailed physical system differ from the flowchart, because the flowchart depicts some detail or some kind of logic, like everything else, either or, whatever that is. So it is different because we don't have this in the data flow diagram. As we see in this slide, the symbols we used in data flow, we could see really 2 different types of system. Either one with the Markov and Jordan symbols, and gain and Sarsen symbols. This figure shows the oval, if you look at it as the oval, which it represents a process. This is in the Markov and Jordan symbol. But if you want to use gain and Sarsen, it is like a square with a curved corner there, and the top piece of it there, that's reserved for the number of the process. 1, 1, 2, 1, 3, 3, 1, 3, 2, whatever. The same for the data store. The data store, a rectangle with gain and Sarsen. Again, it's a rectangle, but a piece of it, the left side piece of it there, again, it's reserved for the number of the database, D1, D2, D3, etc. Source and sink, actually, it is a square, but here even we see it as a rectangle, but it is really closer to the square more than it is to the rectangle. And أخيرا data flow diagram, the data flow, not the data flow diagram, the data flow, it is an arrow, which it is the same in both of them, and we'll see how really this works. As we mentioned earlier, you look at the process. The process, it's an oval. Work or action performed and a data inside the system. Data store, data at rest. Again, it is inside the system, which is to represent either a database or a file. If we look at the source and sink, third symbol of the data flow diagram, it is an external entity, because the source is the one outside the system, and again same for the sink. It's like the report we create, whatever. That's what really they look at it as outside the system, because the source, it has the input which it goes to the system, and the sink, it has the output which it leaves the system and goes to the, like a report or whatever. So we call it here outside the system. Data flow, it is data in motion. It is an arrow moving from one place to another, and it has one direction only. Well, developing a DFD. Context diagram is an overview of an organization system that shows the system boundaries, external entities that interact with the system, and major information flows between the entities of the system. In other words, if we look at the context diagram, we'll see one big oval, or probably sometimes we represent it in other classes, whatever, like a rectangle, or maybe a square or a circle. This is represent the boundary, the scope of the system. And the one outside, the entity, the external entity, as they said here, external entity that interact with the system. External entity, they interact with the system, and it is represent, first of all, as we said, the system, the boundary. Then external entities, the one which is interact. Sometimes those external entities, whatever, it's like the stakeholder, but sometimes it doesn't have to be all stakeholder. But sometimes probably you could have a system, another subsystem interact with this one. We see it as an external entity in this one. Major information flows. The flows, it goes between these entities and the system. Not only one process symbol and no data stored shown. In the context diagram, one process, as we said, one process, either in a can flow or rectangle or square or circle, whatever, and all those arrow goes in and out of that process. Those the one it goes out to the external entity, out comes from the external entity to the system. Here, the context diagram of a food ordering system. Food ordering system, if you look at it, and we call it food ordering system, it is really part of a restaurant system. Restaurant system, it's like look at a restaurant. Restaurant, it has a food ordering system, it has financial system, it has purchasing system, it has the material system, it has the warehouse system. There are many different systems, but those are really a subsystem of the restaurant system. But when you look at that food ordering system, we call it system because we have some definition. For a subsystem, we always say a subsystem, it is a system in its own right. This means a subsystem, it takes really all the right, all the functionality or whatever of that system. Example, if we want to do a kitchen, if we want to do like if we want to have build a university system. The university system, it has registration system, it has library system, it has financial system, it has material system, many different systems. If we take this system and give you one of those like registrations, we call it registration system. We don't say call it registration subsystem, but for you it is really a system because it is really a system in its own right. Looking at the food ordering system as a part of the kitchens, the restaurant system, if you see the zero there with the food ordering system, this is the boundary of that system. If you look at the kitchen and the customer and restaurant manager, those are the external entities. If we look at those, we'll see all these three, kitchen, restaurant manager, and customer, all of them either source or sink. Either source or sink. They are represented by, it should be a square, but here even it looks as a rectangle, as we said in the other square. Source and sink. If we look at the restaurant manager, it's a sink. And kitchen, it's a sink. What do we mean by that? The food ordering system, it creates a report and it goes to the restaurant manager. And that's it. The material went in the report and the report left out the system, and so we call it a sink. The same for the kitchen. The kitchen, no, because in the food ordering system, when you order the food, it will send a note, send a piece of whatever, print something to the kitchen to prepare that meal or that order. But if we look at the customer, it has a source and sink in the same time. As a source, when you give the order to that food ordering system. Food ordering system, it is that boy or that little girl in the restaurant standing behind the cash register, and the cash register program, the one, it is really the food ordering system. If you look at it, you go, you give him, I want 2 hamburger, 3 fries, 2 Coke, whatever. Those goes in the customer order, and you see it goes from the customer to the food ordering system. Those are the parameter. Those are the data in motion. It goes from a customer to the food ordering system. The food ordering system, after it take these parameter, it do manipulate this information, these parameter, add up something, whatever, and then it give you a receipt. The thing behind the food ordering system is doing a lot here. First of all, it goes and update the inventory file. It reduce the inventory file and the item, the one you have in the customer order, like you order like 2 pieces of hamburger. They go to the inventory where that hamburger item, and they deduct 2 pieces of it. And the same for fries, the same for whatever, the same. In the meantime, they go and they update the sales system. They go to the item master and find out the item you order, the price of it, and the quantity, and they send parameter with these to another program inside the food ordering system, and that program take this parameter and update the sales with the total dollar and cent and whatever, and then. In the meantime, as we said, it send note to the kitchen and it create a receipt and give it back to you. So you as a customer, you are a source, you give the customer order and your receipt, you receive the receipt. But the food, this is outside the kitchen, outside the context diagram. Now, if we're going to take the context diagram, the one we saw there, the food ordering system, it is really a subsystem of them, and actually we call it system. But now we need really to decompose it to a pieces. What really those pieces, what these programs, the program which is update the inventory, the program which is update the file, the sales, the program which is write the report, which is whatever it is, the program which it is send write a receipt and send it back to you. What those components are, we need to decompose that subsystem to its part. So level 0 diagram is a data flow diagram that represent system's major processes, data flows and data stores at a high level of detail. The process here labeled as 1.0, 2.0, 3.0, etc. There will be decomposed into more primitive lower level, which it is we're going to go to level 1, level 2, as we said before. Now, the context, it depends on the context diagram. If your context diagram contains the university system, then level 0 diagram is the major entity like registration system, financial system, purchasing system, library system, etc. But if your system or your project is financial system, my program or my project is really financial system. So the context diagram of it, it is the financial system of just. Level 0 of financial system is like accounts payable subsystem, account receivable subsystem, accounting, budget, etc. So we decompose the context diagram to its major entity in level 0. Let's look at level 0 diagram of the food ordering system. Let's first look at the customer and the kitchen and the restaurant manager. Those the one represented in square-like, as we said, because it looks like rectangle, but they are square. Those are the same external entities, the one it was in the context diagram. What is the balancing? Now we're gonna see. In the context diagram, we saw the food order. It goes from the food ordering system to the kitchen. So it is one arrow leaving process 1.0 going to the kitchen. This is one out. And this is another one, management report, which it goes from 4.0 to the restaurant. That's the second one out. And if you go to the customer, you find one in and one out. The customer, the order, the parameter, your order, you as a customer, which it went to the food ordering system, and the receipt, which it goes back. So in this case, if we compare context diagram with the level 0, we could say it is balanced. 1 in and the 3 out. The 1 in is the customer order. The 3 out, one of them is the receipt, the second one is the food order, and the third one is management report. Now, the food ordering system in the context diagram, as we said, we decompose it to pieces. We decompose it to pieces, and here we have 4 pieces and actually another 2 database. The first piece is the one, it's represent here 1 0, receive and transform system customer food order. Then 2 0, update goods sold. 3 0, update inventory file. And 4 0, produce management report. And we have 2 databases, the goods sold file and the inventory file, D1 and D2. Now, 1 0, 2 0, 3 0, 4 0, D1, D2, those are the decomposition of the food ordering system, the one we saw it in the context diagram. We want and we said it is balanced, so everything is okay. The first one, receive and transform customer food, update inventory. So let's assume that the first one is like, a C++ program, the one it has the main program there, is send parameter with the inventory data to another program, update inventory file. Update inventory file, take that one and it's go to the inventory file and update the information, the item master of it there, subtract, deduct some of those, like whatever the items are. Update goods sold, which it's goods sold, the arrow, it goes from 1 to a 2. It is the data flow, it goes in one direction and go to update. Then 4 0, produce management report. Produce management report, the management report, it takes the inventory file and the goods sold file and they create reports. 4 0, and send it back to send it to the restaurant manager. Let's look at really 4.0 and we'll see if we could really go and decompose these further. In our example here, I think 4.0 will be explodable. We could really decompose it down to more function. We'll go to level 1 and then probably some of them we could go to level 2, as we're gonna see shortly. Data flow diagram rules. There are 2 data flow diagram guidelines that apply. The input of a process are different from the output of the process. Process purpose is to transform input into output. So the process, if there is a process and it goes input to it, so the error comes from something, goes inside the process. The output, it goes outside. So we cannot have one data flow with 2 arrow. We cannot have 2 direction. It has to go, you have to have a 2 data flow. One go in this direction and the other one go the other direction. Process's purpose is to transform input into data. Objects in DFD have unique names. Every process has a unique name. Every process has to have really a unique name in order to differentiate it from others. Let's try to read these rules. We actually talk about them. Process. For the oval, no process can have only output. If you see an oval there and there is an arrow, leaves it outside with no arrow going inside that process, there is a problem. As we say here, it is making data from nothing. It's a miracle. If an object has only output, then it must be a source. No process can have only input. As we said, no process can have only output. Again, there is no process can have only input. A black hole, it's like you call a program and infinite loop goes there and they never come back, never send you anything return from that one. If any object has input, then it must be async. A process has a verb process. For the data store, for the database or a file. Data cannot move directly from one data store to another one. Like, if you take information from a database and you update another database, you cannot see data flow goes from database to database, from rectangle to rectangle. I think it has to go, from a rectangle to a process, which it is you read the database, you retrieve the record from the database. So you see the record or the flow, the data flow comes from the rectangle to the oval, and then from the oval to another probably rectangle, which it is updating the database. The update, it leaves the process, go to the database. Retrieve, it comes from the database, from the rectangle to the oval. Data cannot move directly from outside source store. Again, for a report, you cannot see a data flow goes from a source to the rectangle, from square to a rectangle, from a source مباشرة to a database. No, it has to go through again a process. Data cannot move directly to an outside sink. Again, for a report, if you want to have a report, again, you have a process. You have to have a process between. The process, it will take information from the database, so the arrow goes from the rectangle to the oval, and then from the oval to the square, which it is sink, which it represents a report. A data store has a noun phrase. The third one, which is a source and sink. Source sink, data cannot move directly from a source to a sink. It must be moved to a process if the data are of any concern to our system. Otherwise, the data flow is not shown in the DFD. A source sink is a noun phrase label and represented by a square. The last slide, which represent more rules actually for data flow, and the rest of them, and the rest of the information, it comes in the next lecture, That regarding data flow has only one direction. As we said before, data flow, if there is a data flow, goes from process to another process, and there is something go back to it, it has to have two data flow, one going from this process to that process, and the other one leave the second process and go to the first one. So data flow has only one direction of flow between symbol. It may flow in both directions between a process and a data store to show a read before an update. The latter is usually indicated, however, by two separate arrows, because these happen at different times. It happen, the call, and then it return. So you cannot have it. If you have a fork in a data flow means that exactly the same data, the same parameter, goes from a common location to two or more different processes. Data store or source or sink, whatever it is. A joint, it is like the opposite of the fork. A joint in a data flow means that exactly the same data come from any of two or more different process data or data store or source, whatever, to go into that location. A data flow cannot go directly back to the same process it leaves. Data flow, it cannot go directly to the same process. There must be at least one other process that handle the data flow, produces some other data flow, and return the original data flow to the beginning. Here we have a problem how we're going to represent like the recursive function, because the recursive function, the function call itself, actually it is not really a data flow, because data flow, data in motion. The data flow, you see it, the arrow, you see it, it carries a set of data. But when you recursive function, when it call itself again, it doesn't call it with the same parameter. It starts with n, then n minus 1, then n minus 1, and on and on until you get the base thing in the last one. So we could represent it in a different way by having like a 2 or 3 processes, and there is kind of a loop between them. A data flow to a data store means update. if you see a data flow, go to a data store, to a database, this means it is update, delete or change, whatever. A data flow from a data store means retrieve. A data flow has a noun phrase label, it has a name and whatever, and it goes one direction.